All right, on the board states molar mass. That's what we are going to be discussing today. That's what your video was about last Friday. Now, our learning target is to describe how a mole is used in chemistry. That's the same one we had last video also. Now, what's a little bit different is our success criteria. We are going to be able to calculate the molar mass of an element and a compound. Now, it's really easy to do the molar mass of an element, a little bit tougher to do the molar mass of a compound. So, molar mass. Let's talk a little bit about this. And you know what? I didn't say this, but let's take out our periodic table. We're going to be using our periodic table a lot today. The molar mass is the mass of 1 mole in grams. It is equal to the numerical value of the average atomic mass. And we get this from the periodic table. Now, if you remember, way back when, we talked about isotopes. And let's use carbon because carbon's going to be my first example coming up here. Carbon, we stated, had 2 isotopes, carbon-12, carbon-14. And that red number on the periodic table, which yours for carbon should be 12.011, right? That number on that periodic table, this 12.011, is the average of the isotopes, taking into consideration the abundance of that particular isotope. Remember that since that number is closer to 12, we know that there's more of the carbon-12 isotope than there are of the carbon-14 isotope. All right? So that value, it's not a whole number because it's an average of those isotopes with the abundance. All right, so carbon, 12.011. Pretty easy, found that on the periodic table, right? How about magnesium? Is it 24.3050? It is. What about copper? 63.546 grams? Yeah, all right. So that's pretty easy to find for an individual atom. Well, let's check our understanding, okay? Let's check our understanding. What about bromine? Who can tell me what bromine is? Well, apparently everybody can. 79.904 grams per mole. That's somehow, sometimes we say it like this, grams per mole. All right, what about tin? 118.710 grams per mole. Now, what does this mean? Well, let's go back to copper, or excuse me, not copper, carbon. Let's go back to carbon. Do you think that I could find a scale that I could measure 12.011 grams of carbon? Well, I think I could. I think I could find a scale that measured 12.011. Matter of fact, if you look back here in the rooms, that scale right there, those 2 scales will take it out four decimal places for a mass. So they're very precise. All right? So I could find a scale that would measure 12.011 grams. That would be 1 mole of carbon. So if I can find a scale that measures out to the correct precision, can I calculate, can I measure out the moles? How many of a mole of each element? I could. Okay? I could. I could find tin, and I could measure out 118.710 grams of tin. That would be 1 mole of tin. Now, it gets a little bit more difficult when we talk about molecules and compounds. Now, why is that so? Well, Number one, molecules and compounds, we're going to have to write out the formulas. And I preach to you, and I preach to you, and I preach to you. If you can't write formulas, you're going to have problems with this. I even saw that earlier in the day, all right? The mass in grams of 1 mole is equal to the sum of the atomic masses. So if I add up all of the atomic masses of the atoms involved in that compound, then I will have the mass of that compound. I always like to use sodium chloride, all right? Sodium chloride. What's the molar mass of sodium chloride? Well, first of all, I have to find the formula. Sodium chloride's really easy because sodium's a +1, chlorine's a -1, so it's going to be NaCl. So how many sodiums do I have? 1. How many chlorines do I have? 1. So I know that I have 1 mole of sodium, and each sodium mole has 22.9898 grams. Check your periodic table. Is that a correct statement? Yep. I have 1 mole of chlorine. Okay? Chlorine is 35.45 grams. So when I add those two together, I get a value of 58.44. Now, why? Why is it rounded there? Sig figs. Remember, we're adding and subtracting. So that's rounded there based on my sig figs. I see I have 4 places past the decimal over here, 4 places past the decimal. Right here I have 2 places, so it tells me I can only have 2 places past the decimal here. So 58.44 grams. 1 mole of sodium chloride is 58.44 grams. All right? Now, we're going to go in and we're going to work a couple of these. So, you might want to take out your ion sheets too, because we're going to do some ionic bonding here. First one, potassium permanganate. I look at my ion sheet. I need to find permanganate. Permanganate is MnO4, 1 minus. Well, I know that potassium is an alkali metal, so it's going to have a 1 plus. So my formula for potassium permanganate is KMnO4. Now, how I work these, ladies and gentlemen, and I've done this for many, many years, but I still, when I'm working these, I still follow the same procedure. And what I do is I write down all of my elements that I have involved, because I've got to get the sum of all of them. Well, I know that potassium, in my formula, I have 1 potassium. Each potassium weighs 39.0983 grams. So my total of potassium is 39.0983 grams. Manganese. I have 1 manganese. Each manganese is 54.9380 grams. So my mass due to manganese is 54.9380 grams. Now, oxygen's where it's a little bit different, because I can see that I have 4 oxygens. I have 4 oxygens. So I'm going to take 4 times 15.9994, which is the mass of oxygen on the periodic table. I multiply those together. 15.9994 times 4. I'm going to get a value of 63.9976. Now I add all of these values together, and I come up with a value of 158.63 0.0339 grams. So that is telling me right here, that's telling me that 1 mole, 1 mole of potassium permanganate would weigh 158.0339 grams. Now, could I measure that many grams out? Yep, so I could measure out 1 mole of potassium permanganate. What would 2 moles be? Double it, right? Okay, double it. Diphosphorus pentoxide. Oh, the prefixes, a little covalent bonding going on here. So, diphosphorus pentoxide, P2O4. Once again, the way I do this is I write down, I have phosphorus involved, I have oxygen involved. I have 2 phosphorus. Each phosphorus has a mass of 30.9738 grams. So my total mass from phosphorus is going to be 61.9476 grams. Oxygen. I have 5 of them. I have 5 of them. Each one is 15.9994 grams. So my oxygen is going to be 79.9970 grams. I add them all together and I get a value of 141.9446 grams. So 1 mole of diphosphorus pentoxide weighs 141.9446 grams. Yes, ma'am.
When we're labeling these, do you do just grams or just 4 grams per mole? What should be like first?
Well, when we're going to see, that's a great question. Should I label it grams or grams per mole? Where we're going to see that grams per mole bit is when we need to factor out and cancel, okay? So you would be okay just to put 1 mole of P2O5 equals, okay? That's really what we're saying there, okay? That's really what we're saying, but you're eventually going to have this over a mole in order to cancel on our factor label method, all right? Does that answer your question? Our next one. I put this one on here because of this ammonium. Now, I recognize ammonium is a special one of my polyatomics. It's NH4 plus 1. So I know that if I have ammonium sulfate, or excuse me, sulfide, I'm going to have NH4 parentheses 2 S. I put that on there just to make sure we knew how to work the parentheses. NHS. Okay? NHS. So I know that right here, this nitrogen is like having 1 of them. But since I have parentheses around it, how many do I have total? 2. So I have 2 nitrogen. Each nitrogen is 14.0067 grams. So my total mass of nitrogen is 28.0134 grams. Now my hydrogen, 4 of them, plus the 2. Nope, it's not 4 plus the 2, it's 4 times the 2. I see that common mistake. So 4 times 2 is 8. 8 times 1.0079 grams is going to give me 8 0.0632 grams. Finally, my sulfur, I have one sulfur. Each sulfur is 32.065 grams. 32.065 grams. So 4, 4, 3. I'm going to make sure that my answer has 3 past the decimal point for my sig figs, and that's going to give me 68.142 grams. So 1 mole of ammonium sulfide weighs 68.142 grams. Now what I want you to do, I want you to work this one, and then I'm going to work it on the board when we're done with it. So you work this one in your notebook. I'm going to walk around and help if I need to help, but work this one in your notebook, then I'm going to work it on the smart board. All right, we've got some great discussion going on here. Now, I put this on here for a reason, and that reason is to show you that if you can't write the formula, I look at this and I have to convert back to my acid rules. So IC 1 or 3. This is acid rule number 3. So this is telling me that I'm looking for selenate. Selenate on my polyatomic ion list. Oh, where are you? There you are. It is S. It is SeO4, 2 minus. Now that tells me that I need to have 2 hydrogens because of that 2 minus. So selenic acid is H2SeO4. So I would say of the folks up here, probably named it wrong. Okay? Probably named it wrong if you had different values. Now, that leads me right along, same thing, HSeO. 1 times 1.0, excuse me, let me check that, 2 times 1.0079. That gives me a value of 2.0158. Selenium. I have 1 selenium. Each selenium is 78.96 grams. 78.96 grams. Oxygen. 4 oxygens, 15.9994 grams. So that's going to give me 63.9976 grams. When I do the math, I can see that I'm going to have my sig figs at not the 10th, but the 100th place. So when I did my math, I came out with 144.97 grams. Now, how many people give me a thumbs up on that? They got it. Okay. Now, I would almost bet money that you're not going to have problems adding and multiplying these in your calculator. So where you're going to miss this is right here. Right here. Writing that formula is where you're going to miss this. So make sure, once again, I'm going to preach it again for you. If you're struggling with formulas, get help, or you're not going to do very good on this stuff. Please. Any questions for me?